Hi, my name is Madison Audette, and today I will be talking about the enzyme maltase, and in some portions of the presentation, taking a step further by looking at a version of the enzyme known as maltase glucoamylase. In today's topic overview, we will cover ideas related, but not limited to, a brief overview of presentation 1, the overall mechanism and catalytic strategy of maltase, and finally, some experiment probing effectiveness of maltase and/or maltase glucoamylase. Now that we know what the topic overview will bring for this presentation, I would like to recall some ideas from presentation 1. From the last presentation, we can remember that maltase is found in the brush border cells that line the intestinal wall. We can see that in the image to the left where it sits right on top of the brush border. However, we can note that in the cell, maltase is specifically located on chromosome 7. Next, we can recall the functions of maltase. The two most important functions of maltase is to 1, catalyze the hydrolysis of the disaccharide maltose into molecules of alpha glucose or monosaccharides. And secondly, its function is to function as an alternate pathway for starch digestion. It's important to note this only occurs when the body lacks alpha amylase. We also would like to note why this is important to us, in which we can remember that without maltase, we'd be unable to break down maltose into glucose molecules, and glucose is essential for the body as it is used for energy or storage in the liver as glycogen or animal starch. In addition to this, with the lack of maltase or a deficiency in maltase, we would expect to see a wide variety of digestive complications because the starches and sugars would become more difficult for the body, in turn leading to a number of side effects and digestive issues. The last thing we want to note is how maltase is measured, which is usually done by running enzymatic assays. If you recall from presentation 1, they ran a routine assay by taking equal amounts of substrate and enzyme and running it in a buffer, then used results along with a glue kit to compare against a standard glucose curve. Finally, the Km, Kcat, and Vmax values were measured using a Lin-Weaver-Burke plot. From this, we can recall Vmax was 29.8 micromoles per minute, Km was 0.9 millimolar, and Kcat was 2.03 per minute. The last thing I'd like to refresh you all with is the structure of maltase. This is an example of the N-terminal subunit of maltase found on RCSB using code 2QLY. From this, we want to note there are approximately 10 alpha helices and 30 beta helices. We also can note there are 2 active sites in which we will look at closer a little later. Lastly, it's important to know there are 2 subunits of maltase, both the N-terminal and the C-terminal subunit. However, again, it's important to note that this structure example is only showing the N-terminal subunit. Since we are talking about the structure of maltose and its active sites, I feel this is a good time to look at maltose versus lactose, since I didn't mention it in the last presentation. Looking at the image to the right, both maltose and lactose look quite similar, but there are some significant differences. For starters, lactose is hydrolyzed into 1 molecule of glucose and 1 molecule of lactose that are joined via a 1,4 beta linkage, whereas maltose is hydrolyzed into 2 molecules of glucose that are joined via an alpha 1,4 glycosidic linkage. This is important to note because lactose has a beta linkage. Maltase is unable to even come and protonate the oxygen, which I can explain more in the next slide. In addition, maltase has an extreme affinity and desire to bind with the substrate maltose, similar to lactase's affinity to bind with lactose. The reaction between lactose and maltose, or even lactase and maltose, would just not occur. Like I said, lactase is able to break the beta linkage of the glucose molecules, but maltase cannot. It can only hydrolyze the alpha linkage of maltose. With that being said, we can go to the next slide to view the overall reaction. Here we can see the overall reaction of maltase and maltose. First, we can note in the reactants that 2 glucose molecules of maltose are joined via an alpha 1,4 glycosidic linkage. This is where I was explaining the difference between maltose and lactose, which lactose has a beta linkage right where this alpha linkage is. From here, we can also see that there's water present in the reactants. This is necessary because lysis literally means to break and hydro is water. So it literally means using water to break the alpha 1,4 glycosidic bond of those 2 glucose molecules. This then gives us our products, which is 2 separate alpha glucose molecules. In the next slide, we will take a further look at how the hydrolysis actually works. Now that we've looked at the overall reaction, we're going to look at some nitty-gritty stuff, and we're going to look at the mechanism and the catalytic strategy. And I'm going to couple those two concepts, and you'll see why in a few minutes. So if we can recall, the initial structure of our maltose molecule is two glucose molecules, and it's joined by that oxygen at that alpha-1,4 glycosidic linkage. And we also have our water present. This is a hydrolysis reaction, so we should remember that that's present. And then from there, we also have a histidine 489 present in the active site. And this histidine 489 has a positive charge on it. It's going to act as an acid for acid catalysis. And what it's going to do is it's going to protonate that oxygen at the alpha-1,4 glycosidic linkage, and it's going to form an alcohol. So now our next molecule is our two glucose molecules, and instead of being joined by just that oxygen at the alpha-1,4 glycosidic linkage, we're going to have an alcohol there. We're also still having our water present. The next step is that one of those glucose molecules is going to take that alcohol with it, and that's one glucose molecule already formed. And our other glucose molecule is going to take its electrons, and it's going to form a resonance stabilized structure. And we still have our water present, and this is where it's going to come in. Our water is now going to act as a nucleophile, and it's going to attack from underneath at that carbon 1 of that resonance stabilized structure. Now that water is attached to that structure, it wants to deprotonate, it wants to give up a hydrogen. So what it's going to do, it's going to give that hydrogen back to that histidine 489, because that histidine 489 is still sitting there waiting for its proton, because we also have aspartic acid 414 present in the active site, and it's forming a salt bridge with that histidine in order to stabilize it while it waits to receive its hydrogen back. So once that water deprotonates and gives up its H back to histidine, we have now formed our two glucose molecules, sorry. The last thing that we should note about the mechanism, we should note that the rate limiting step of this process is the release of product from the active site. This is probably the most common rate limiting step in a number of enzymatic reactions, and it is including for maltose hydrolysis. Now that we've looked at the overall mechanism and catalytic strategy of maltose, I'd like to take a step further and see how this changes with an inhibitor present. So I found this study done by some researchers, and they decided to look at the substrate specificity, active site differences, and overall inhibition differences. Before I talk about that, the researchers wanted to first note some important key factors. First, this is maltase glucoamylase, and in this version of maltase, there are two subunits of this enzyme, a C-terminal and an N-terminal. The researchers wanted to note some important information they knew going into this experiment. The first and most important being that arquebus is a competitive inhibitor of the MGMC subunit and can actually be found within the active site of MGMC. The main reason for this is due to active site differences between the two subunits, which I'll explain some here and some in the next slide. First, the subsites of MGMC expand from -1 to +3. We will see why this is crucial in the next slide, but stick with me for now. The next thing to note is that there are both numerous hydrogen bonds and hydrophobic reactions between the MGMC subunit and arquebus. The most important one to note, though, is the residue of ASP 1526, which actually forms one hydrogen bond with the atom N4B of arquebus. This in turn makes it a candidate for an acid-base catalytic residue. This will be essential to the overall inhibition process. Now that I've discussed some of the important factors between MGMC and arquebus that the researchers noted, they next wanted to take the information they already knew and compare it to the MGMN subunit. More importantly, looking at kinetic data, inhibition, substrate specificity, and structure differences. Now that we have some important factors of this experiment and how MGMC interacts with arquebus, it is now time to look at how arquebus reacts with MGMN and how the two subunits compare. One of the first things noted between the C and N terminal was there are different binding constants for substrates, indicating major differences that exist in the active sites of MGMN versus MGMC. For example, MGMN preferred binding constants G2 through G6, while MGMC did not. In order to look more clearly at differences between the two subunits, they used an arquebus structure with 4 rings. From this, they were able to determine The arquebus with the 4 rings displayed much higher inhibitory activity against MGAMC than against MGAMN. This then suggested to researchers that MGAMC has a higher binding affinity for substrates that are longer than MGMN does. Now that the researchers looked at differences in the substrate length, they decided to then look at the actual subunits themselves. From there, they determined that when comparing MGMC with MGMN, they noted that MGMC had 21 extra residues. These residues ultimately complemented the structure by folding into an alpha helix and a loop in the active site. Together with other components of MGMC, there were 2 active subsites at positive 2 and positive 3. These subsites were crucial because they're able to look deeper and notice that these extra 21 residues made a substantial contribution to stabilizing the 3rd arquebus ring at the positive 2 subsite. These results were able to allow researchers to know that the extra 21 residues made significant contributions to the binding of MGMC with longer substrates. From here, the researchers already knew of the contribution of the extra residues made, but they went ahead and wanted to see how big of a difference it actually made. The researchers then generated a version of the MGMC subunit and deleted the extra 21 residues. By doing so, they were able to determine that those residues removed also removed the positive 2 and positive 3 subsites, in turn altering the specificity of the enzyme, giving it similar substrate specificities of the MGMN subunit. The researchers concluded that the additional subsites in MGMC account for the preference for longer substrates. Now that researchers have clearly identified some of the major differences between the 2 subunits, let's look at how this can be important to us and how these measurements and findings were actually determined. In order to better determine some of the kinetic data to clarify and confirm the scientists' conclusion about the different specificities and the different inhibitory reactions between the 2 subunits, they had to get some kinetic data. And like most enzyme reactions, in order to get that kinetic data, they run enzymatic assays, and that was what was done here. So these scientists, they took a total volume reaction mixture of 20 microliters, which contained equal amounts of the substrate and equal amounts of the enzyme. They then diluted this in a buffer, and the mixture was then incubated. They then used what's called a glue kit, which is pictured to the right, and it was added to each well, and this helped them to determine the amount of glucose produced in the reaction. They then were able to measure the absorbance and compare the results to a standard glucose curve. Finally, they were able to get some of the kinetic data by using a Lindweaver-Burke plot. And the last thing to note is when they did this with the inhibitor present, they measured the amount of glucose production using maltose as the substrate, but they also used the same procedure as above, just with the inhibitor present. Now that we've looked at the study and how it was carried out, along with the kinetic data, it's safe to say there are kinetic differences between MGMN and MGMC. Okay, but why is this important to us? Well, because arquebus is used in patients with diabetes and obesity, the information provided can be used to generate highly efficient inhibitors for said diseases. Okay, what do I mean by this? So, for example, MGMC has a smaller KM-KCAT ratio. This indicates a slower catalytic process. This is key because we want that inhibitor to slow down the process as much as it can. So since arquebus is used to control blood sugar in diabetes patients, it's essential that arquebus inhibits and slows down the catalytic process, as I just said. So from there, we can note that MGMC is a more efficient target for this arquebus inhibitor, because if we look at the KM-KAT ratio for the N-terminal, we note that it's much higher than the C-terminal. And I'm going to explain a little bit why this is more important to us and how it can be used in the real world. So I'm going to look at the image to the left, and this shows us without arquebus present versus with arquebus present. We obviously want to look at the differences, but I want to note the side with the arquebus present. And what we can note from here is that it slows down carbohydrate absorption because maltase is unable to break down that maltose at its normal rate. Carbohydrate absorption happens at a slower rate, and this is crucial to diabetes patients as they want slow reabsorption to have a consistent, slow, steady rise in blood sugar and avoid spikes or drops. So now that we can confirm that, we can use this information to generate more highly efficient inhibitors for diseases such as diabetes and obesity. The last thing I would like to conclude with is to draw on how this inhibition example relates to the overall mechanism of maltase. The first thing I'd like to recall from the mechanism is how it functions. Maltase is an enzyme in which functions to speed up a chemical reaction. Specifically, as mentioned in the mechanism slide, maltase will bind to the substrate maltose in order to catalyze a hydrolysis reaction. However, with an inhibitor now present, it prevents this from occurring. The inhibitor, arquebus, will instead compete with the maltose substrate for a position in the enzyme. When the inhibitor wins, in which we have seen it does, it will gain its position within the enzyme. If we recall the lock and key example, we note the substrate acts as a key and the enzyme is the lock. However, with the inhibitor present, it can act as a key still, but instead is unable to open the lock or the enzyme. Hence, the observed reaction is now slowed down because some of the available enzyme sites are now occupied by the inhibitor. So to clarify, I would not say the presence of the inhibitor supports the mechanism, but instead opposes it. The overall mechanism is the same, but instead of maltose binding to maltase to catalyze the hydrolysis, arquebus is replacing the maltose substrate and binding with the enzyme. The difference is maltose is the actual key and can unlock maltase to catalyze the hydrolysis reaction to occur, but arquebus is only a partial key and can only attach to maltase but not unlock it, preventing and slowing down the overall hydrolysis reaction. So I will leave you with this. The overall mechanism of maltase is not exactly supported with an inhibitor present, but is instead opposed. However, the inhibitor does function similarly to maltose, which does support the mechanism concept. Now that we've gone over everything on the topic overview, my final slide just displays some of my work cited. I would like to thank everyone for listening and hope everyone has a good day.